In the video just previous to this, we established what we call the phasor form of the traveling wave equations. And for voltage, that was V of Z. The phasor voltage on the transmission line is equal to V bar plus e to the minus gamma Z plus V bar minus e to the plus gamma Z. And an analogous current phasor traveling wave equation existed that was just I bar plus e to the minus gamma Z plus I bar minus e to the plus gamma Z. This was in volts and this was in amps. This really is a voltage. This really is a description of current. Over here, I've written these out as the traveling wave equations in the time-dependent form. The only difference here is that V bar plus in this equation has been written as V0 plus. I did that because a lot of times if you look at ancillary text, reference text, or things like that, this is the format you're going to see. I personally don't like that because it doesn't indicate that there is a phase shift associated with V0 plus. There really should be a bar over it to indicate that it has both a magnitude and an angle associated with it. It's hard to tell that that's that, whereas if you look at this, okay, I can tell that it's a phasor quantity because it's got that it's got the phasor notation V bar over top of it. So in my lectures, I tend to use this format. If you are looking at Wentworth, which is the reference text, you're going to see this format. So just know that those are equivalent, and probably goes without saying, but I bar plus is equal to I0 plus. V bar minus is equal to V0 minus, and I bar minus is equal to I0 minus. So just note that all of these quantities have magnitudes and angles associated with them. And that's where the phase shift would come into the cosine wave forms for all here. That's why there's no phase shift indicated there, because it's contained in those multipliers out front. So the problem is with these equations is we don't know what these values for V0 plus, V0 minus, I0 plus, and I0 minus are. We don't know. So we have two equations and two unknowns. And so our next steps are that we have to start beginning to solve for these values here. And the first way that we're going to do that is we're going to return to that concept that I introduced when we were discussing bounce diagrams called the characteristic impedance. So what I'm going to do next is use the wave equations to derive characteristic impedance, and that's going to allow us to simplify the traveling wave equations to something that's a little bit more usable. To do this, the first thing I'm going to do is take the positional derivative, or the derivative with respect to position of the voltage traveling wave equation. So I'm just going to say take the derivative of both sides of that, and it's going to be the derivative of the phasor voltage with respect to position is just going to be V bar plus times the derivative of e to the minus gamma z, and we can use the phasor derivative technique here, so we just need to pull the constant out here, so that's minus gamma times e to the minus gamma z, and then we add on v bar minus, and we can use the phasor derivative technique here. Here the derivative of e to the gamma z is just gamma e to the gamma z. We don't have a negative in the exponent, so we just multiply that by gamma e to the gamma z. So we've got the derivative of the traveling voltage wave equation in phasor form is what we've taken there. So if you recall from our analysis, our initial analysis of T-lines, from KVL, we also had another statement for the phasor voltage derivative, and that was in terms of the transmission line parameters R prime and L prime. And this equation that I just rewrote here, we developed several slides ago. from KCL as applied to a transmission line. So what I can do is I can just equate both sides of these equations. So I can just plug these in, right? And so if I were to write that all out, I would get, I'm going to just pull the minus gamma out front, minus gamma v bar plus e to the minus gamma z, so that's this part, plus gamma v bar minus e to the plus gamma z, so that's this equation, is going to be equal to minus, oh, I put the minus sign right here in the wrong spot. It should be minus quantity r prime plus j omega l. Minus r prime plus j omega l prime. And then I'm just going to go ahead and substitute in the phasor equation here for current. So that's going to be I bar plus e to the minus gamma z plus I bar minus e to the gamma z, or e to the plus gamma z, however you like that. So what I'd like to do next is that I'm going to divide both sides by r prime j omega l prime. What that's going to result in is this cancels out here, and it just shows up in the denominator over here. And then I can also distribute this minus sign here, and so if we get rid of the minus sign, we lose this here, and we get this. And then the last thing I'd like to do is factor out this gamma from both terms. So we've got gamma times that whole quantity. So we're left with gamma times v bar plus e to the minus gamma z minus v bar minus e to the gamma z divided by r prime plus j omega l prime is equal to I bar plus e to the minus gamma z plus I bar minus e to the gamma z. So we've done that rearranging. So what we're going to do next is we're going to equate the exponential terms. So we see that we could rewrite this side as gamma v bar plus e to the minus gamma z over r prime plus j omega l prime minus gamma times v bar minus e to the gamma z over r prime plus j omega l prime. All I've done is separate out the numerators of the left-hand side of the equation right there. And this has e to the minus gamma z, and this has e to the minus gamma z. This has e to the plus gamma z, and this has e to the plus gamma z. So what we can say is that I bar plus has to be equal to this portion right here. So I bar plus has to be equal to gamma v bar plus over r prime plus j omega l prime. And similarly, I bar minus has to be equal to everything that multiplies by e to the gamma z, which is minus gamma v bar minus over r prime plus j omega l prime. So we determine those by equating the multiplier of the exponential natural number here. So what I want to do here is solve for the ratio of v bar plus to I bar plus, and this just becomes v bar plus to I bar plus is equal to r prime plus j omega l prime over gamma. And if I solve this guy, I find that the ratio of v bar minus to I bar minus is equal to minus R prime plus J omega L prime over gamma. Now you'll recall that gamma is just a simplification of something we defined earlier, which was R prime plus J omega L prime times G prime plus J omega C prime. So I can plug this in for gamma in here, and what that will result in is V bar plus over I bar plus, is going to be equal to the square root of R prime plus J omega L prime over G prime plus J omega C prime, and V bar minus over I bar minus is going to be equal to the opposite of that. And we define this quantity underneath the radical as the characteristic impedance of the transmission line. So the characteristic of the impedance of the transmission line by mathematical analysis is the ratio of either the forward traveling voltage wave to the forward traveling current wave, or the reverse traveling voltage wave to the reverse traveling current wave. Remember, at any given time, both of these exist, and so Z0 is not the total voltage to total current, it's forward voltage to forward current, or reverse voltage to reverse current only, not totals. I see that mistake made pretty commonly. So I've summarized that up here. If you're given the traveling wave equations, we can relate forward voltage and forward current and reverse voltage and reverse current through the characteristic impedance, and Z0 again is just easily solved for from the distributed parameter model as R prime plus J omega L prime over G prime plus J omega C prime.